So I'm preparing a contribution to the ITUT Q420 uh, called Framework for Ensuring Trustworthiness of AI Data Across Heterogeneous Computing Layers for Intelligent IoT Services. It's going to be presented by Professor Hong, and I prepared the PPT and as well as the Word document, the formal official document for contribution to ITUT. And the presentation file goes like this. The first page starts with the problem definition. So AI services are distributed and operated across heterogeneous computing layers, obviously. So the quality of AI data generated and consumed at each layer it varies. And then as a result, errors or biases at one layer can overflow to the other layer. As a result, it can impact the overall service performance. And in the end, an end-to-end trustworthiness framework is required to ensure reliable interoperation across heterogeneous layers. That was the problem definition, and then we're going to discuss about distributed AI model structure. So this is almost typical structure layers. It starts from device layer, which will be deployed at the local element, the device, and then it's going to be integrated as a integrated information at the edge server located in edge layer. And again, those information will be gathered together at the cloud layer be to be treated as input to the large-scale models, historical and regional patterns analysis, and or mapping, of course. For example, root cause analysis and long-term predictions will be conducted at the cloud layer. So the different types of AI data are collected and processed at each heterogeneous computing layers, and trustworthiness standards vary accordingly. So, and then challenges of trust propagation should be considered at this picture. So incomplete and contaminated data from lower layers, for example, devices may propagate to the edge and cloud layers. Conversely, data drift or inaccurate model updates at the cloud layer may negatively impact models at the edge and device layers. And this poses a risk of reduced inference accuracy and overall system safety. And the next challenge is in propagating trustworthiness. Incomplete or contaminated data from lower heterogeneous computing layers may propagate upstream and affect upper layers. Conversely, data drift or it's Like data trustworthiness risk factors. And I just remove one slide because it's almost duplicated. The contents of those two slides are duplicated, and one of them I just got removed because this slide is better in my opinion. And the next slide is about AI data trustworthiness risk factors. At the device layer, sensor errors, data contamination due to adversarial attacks, kind of problems can be exist. And at the edge layer, a regional bias impact from neighboring nodes with low reliability can affect the model. And the cloud layer drips in historical data, model contamination or degraded performance can impact the implementation or deployment of the algorithms, the software behavior. And in common, uh, the labeling errors, spoofing, data drifting, temporal distortion can occur at any layers. Examples of trust matrix need for a framework definition of data trustworthiness criteria. Define quality matrix for AI data used in each heterogeneous computing layer. Trust status propagation structure. Attach tags to indicate the trust status of data processed at each layer. Upper layers receive the tags and validate or filter accordingly. End-to-end tag means metadata. Uh, for example, the reputation of the information scored by the historical data, counted, estimated by the colleagues or by the edge or cloud server. End-to-end verification and recovery loop, those things. And framework overview, 3-layer data quality checked at each layer and matrix are shared. Data moves between layers, trust indicator, meta information are transmitted together. So abstract frame architecture has been defined like this in the picture. In those layers, each layer has their management models, management modules. For example, device AI layer, data trust validator, confidence filter, and schema validator. Those things. In right-hand side, there are two vertical boxes. One of them is the trustworthiness matrix management subsystem, and the other one is feedback and recovery management box management subsystem. So feedback. From edge layer to the device layer, sometimes it can reject, the edge server can reject invalid data from the device layer, and it can alert local model you are getting astray, something wrong in your prediction result. In from cloud layer, they can tell to the edge layer, uh, you should update edge model or adjust model parameters, some information, some orders can be flow down from cloud to edge, or the edge can give order to the device directly, for example, such as the orders such as retrain local model should be retrained, or the model output should be fixed. Some, something like that. So what a fixed model output more specifically? This is a short-term or temporary fix used when the model's output is found unreliable or faulty at runtime, but retraining is not immediately feasible due to the time, compute, or data constraints. Instead of retraining, the system overrides, corrects, or patch fix model output. The output to avoid a wrong or dangerous response. Techniques include applying rule-based corrections using fallback heuristics, using a confidence threshold to suppress low trust outputs, incorporating feedback from cloud-validated sources to adjust the decision. Example, if a model misclassifies a traffic sign and the confidence score is low, the system might ignore their output or substitute it with cloud-derived context, preventing the vehicle from making a wrong turn. Those things. Yeah. Then we're gonna discuss about example framework operation flow. This is a general flow, and specific use case can be use case uh, has been created to explain the flow of the framework. So the representative use case is about autonomous driving, of course, and traffic flow control. So bottom below, it starts from vehicle device, and information will be propagated to the upper layer, which is edge server, and then propagated to the third layer, cloud system. So device detects high confidence events, try to detect edge, try to increase trust through comparison across multiple vehicles and events. Cloud will validate using historical and validates those information using historical and external data. And again, device will execute actions such as suggesting detour routes, kind of things. And these are the um, sub-use cases for each layer. Will be conducted at each layer. And we're proposing the standardization elements such as we're planning to complete the framework architecture. At this stage, we are suggesting only abstract framework structure. It's incomplete, obviously, but it's going to be completed by doing this research to ensure reliable AI data linkage across heterogeneous computing layers. Reference and link to data reliability matrix from other organizations. For example, ITSI. They are discussing about reliability matrix about AI data. And we're gonna expand applicability to various AIoT domains. Applicability of this framework to various AIoT domains. And we're gonna plan to enhance and diversify scenarios based on future real-world validation. Thanks. Yeah, that's all.